All right, good afternoon, chemists. We'll get started now. We started chapter 6. Yes, this is the chapter of the memes, where we'll finally understand why is the cat in the box and why is it dead and alive at the same time. Hopefully, after learning about some of the concepts of, the weird things that happen with electrons because they're so small, we'll elucidate some of these funny memes and comics, so when you are at a party with chemists and physicists, you too can laugh along with us. So let's do one. We left off using our wavelength equations and Planck's constant to understand the relationship between the wave nature of light and the particle nature of light, the photon. So let's just do one more example. So this time with a red laser pointer, right, where we can talk about light in terms of its wave properties, but also its particle properties. So I have some laser pointers with me. So so here's my red laser pointer, all right? So this laser pointer has a certain wavelength. We can calculate its frequency as well. But we can also talk about the energy of the photon in terms of a joule amount, or even a kilojoule per mole amount. So let's describe this light in a comprehensive way, all right? So a red laser pointer, this one, has a wavelength of 650 nanometers, or 650 times 10 to the negative 9 meters, same thing. So with this information, and the idea that light travels at the speed of light, let's first calculate what is the energy of one photon of this light, right? So if we want to calculate the energy of one photon, can I just use this equation? Can I just use this equation, E equals hc over lambda? Can I use it? Yes, we can, because I'm asking you what is the energy of one photon. So we can simply just say, okay, the energy of that one photon that is shining out of this laser pointer is equal to hc, so wavelength, Planck's constant times speed of light divided by wavelength, which we are given. So we plug in those numbers, 6.626 times 10 to the negative 34 joule second. Speed of light, so 3 times 10 to the 8 meters per second over the wavelength that's given, 650 times 10 to the negative 9 meters. And so you see meters cancel, seconds cancel, and you do in fact get a value of joule out. But this is the energy of just one single photon. One photon that comes out of here. So let me just calculate this, negative 34. Times 3 E8 divided by 650 E negative 9. So I get that the energy of one photon is 3.06 times 10 to the negative 19 joules is one photon, right? That's a really tiny energy, right? When we think about light and what it contains, do we ever just interact with one photon of light? No, kind of like atoms, right? We're always interacting with many, many, many of them. So you can think of light as a wave. We can describe it using its wavelength, or we can think of it in terms of a photon and its energy associated with it. So like atoms, anything that we work with in a very, very large magnitude, we can talk about the energy of one of those things, the mass of one atom. But when we're in lab, we always work with tons and tons of atoms. So let's scale this value up to a mole amount, just like our gram amounts for atoms themselves. So we can convert this energy of the laser to kilojoules per mole as well. And this follow-up question is always harder for students to understand, but just recognize that we calculated the energy of one photon. So let's just scale that value up. So if one photon has the energy of, 3 times 10 to the negative 19 joules, so that's one photon. To get a mole amount, we just have to recognize, okay, in 1 mole of photons, I must have 6.022 times 10 to the 23 photons. And so if you look closely, you see that single photons cancel, and we are left with a mole amount of photons. Go one step further and just say, okay, there's 1,000 joules in every 1 kilojoule, and then go to town there. And you see that 6.022 E23 divided by 1,000, you get that this laser has an energy output of 184 kilojoules per mole. So I don't know about you. If I was laser shopping and looking at energy values, what number just looks nicest to our eyes? 184? Yeah, that looks pretty nice. Versus what, 3.06 times 10 to the negative 19? Is that number very nice to our eyes? No. And so this is why scaling these values up into a different unit, like kilojoule per mole, where we use Avogadro's number, convert to kilojoules, is useful, especially with laser shopping, in terms of visible light lasers. Okay, so that is for a red laser pointer. This is a common exam question where I give you wavelength, I have you convert to a different unit, including kilojoule per mole. The harder question is doing it in reverse. If I tell you, here's the energy of my laser, what is the wavelength? That's a harder question, but it really is the same thing, but in reverse. So I'll point that out. We'll do some example questions about that later. All right, so that's where we left off. Oh, wait, did I do this one? Oh, did we want to do another one? Okay, yeah. Oh, yeah, look, yeah, let's do that. I totally forgot what I planned to do. Yeah, so let's do the harder one. All right, so in this one, I have a green laser. And this time I went laser shopping, and I have a green laser. Okay, that one's out of batteries. This one? What? They just said they changed the batteries. Okay, green laser, yes. And it has an energy output of 239 kilojoules per mole. Tell me, what is the wavelength of this laser in nanometers? So we just did it in the forward direction, so now we need to work our way back into reverse. So the idea here is when we use this equation, E equals hc over lambda, we're using the energy of 1 photon. Can I just take this number and shove it into this equation? No, because this is the energy of not 1 photon, but a mole's worth of photons. So we got to undo that per mole amount and calculate what is the energy of just 1 photon. So how to do this? There's a couple ways to do this. How do I want to do it? I'm going to start with 239 kilojoules per 1 mole of photons. All right? And recognize, okay, in 1 mole of photons, I have 6.022 times 10 to the 23 individual photons. And then I need to convert kilojoules to joules, so 1,000 joules. And so doing this should give me the energy of 1 single photon, 1 packet of light of this green laser. And so I get, oops, that is not right. 239 divided by 6.022 e to the 23 times 1,000. Should be a tiny number, so 1 photon is 3.97 times 10 to the negative 19 joules. So that is for 1 photon. This number, am I allowed to put this number into my hc over lambda equation? Yes, I am, because this is the energy of 1 photon. So putting that together, E equals hc over lambda. I have E, energy of a photon. I have Planck's constant. I have speed of light. So I'm just solving for wavelength here. If you rearrange this, because I'm trying to be lazy, hc over energy, I have all of those terms. So 6.626 times 10 to the negative 34 joule second. Speed of light, 3 times 10 to the 8 meters per second. Energy we just calculated of 1 photon is 3.97 times 10 to the negative 19 joules per photon, right? And so if you see here the units, how they cancel, joules cancel, seconds cancel. So when we calculate wavelength, what unit comes out? What unit comes out? Just meters because speed of light is in meters per second. So let's do that, 6.626 e to, wait, I already know the answer. It's, all or no, yeah, I think it's 490. I should probably check. I wrote it. 34 times 3, E8, divided by that, is it 490? No, it's 500. Okay, I was wrong. So the wavelength that comes out is 5 times 10 to the negative 7 meters, but we want this in nanometers, so 1 times 10 to the negative 9 meters is 1 nanometer, so that means the wavelength is 500 nanometers. So this question, I don't know, just does more poorly than the other one. The other one, most students will get right, going from wavelength to the unit of kilojoules per mole, but for some reason going the opposite direction is a lot harder. I wrote a question for 1210 last year, and it was exactly this one, I'm pretty sure. Like I gave a kilojoule per mole value, and I asked what the wavelength is, and I think it was like 30% of students got it right, or something like that. It was really poor. I was surprised because I used my favorite wavelength of light color, and I thought that would help, but it did not help them. So going from this direction, kilojoules per mole to single photon for some reason is harder than scaling it back up. So I just wanted to add a little bit more practice here before moving on. All right, good? Math? Yeah? All right. So that's like the rest of the math. We're gonna talk more about conceptual stuff now and how why electrons are important in addition to light. So the basis of this chapter is that how light interacts with matter is how scientists understood and learned more about the electron. We can't see electrons, we can't see atoms, but we can see light. So if we, shine some light on an object and observe what comes off, we were able to deduce some ideas about what's going on in the electronic structure of our atom. So these were the notable experiments. One of those is the discharge tube, right? So the discharge tube is where you take a gas, usually it's a noble gas, you put it inside a vacuum tube, you shove a bunch of electricity at it, and it shines. If that sounds like a neon sign, and that's because a neon sign is a discharge tube, right? So these gases are just being excited and they give off light, just like a neon sign. And so what they found is that different elements, depending on what gas was inside this tube, they would see different colors, but it wasn't a continuous color of the rainbow. No, it was, if you looked at the color of this discharge tube, only certain lines of the visible spectrum was seen when the light was sent through a prism. And so what you see here, helium has these unique lines in its line spectrum. Neon has another set of lines. Every element has a unique set of visible lines unique to itself. Regardless of who prepares the discharge tube, any neon sign will have the exact same lines within its line spectrum. So what scientists did was looked at these lines and tried to come up with some type of model that explained these lines. Yeah, we can just say like, oh, there are these magical lines that come off when you excite an element, but the marvel of science is, okay, let's come up with this model that not only explains the phenomena that we're seeing, the observations that we're seeing, but also agrees with everything else that we've seen in our universe so far. And that's what's taking us to the next step of quantum theory, quantum physics, and basically the absolute most correct version of our atomic model today. And that is, getting us close, is our Bohr model. Right, so the idea here is that, how light interacts with matter. Here we're seeing light being ejected or emitted from matter, and this is what we are observing. We are observing the light coming off of the matter. That is why light is important here. All right, so how scientists came up with an idea to explain this was the Bohr model. So remember, up until now, we went from the billiard ball model, so we just had like solid spheres. Then we had the, the cookie model, the plum pudding model, and then we had the Rutherford model, right? Where we just had like a diffuse electron cloud and a really dense nucleus. So the next step was the Bohr model, where we gave more structure to the electrons themselves. And this is the new structure that we put in with the electrons. That no longer is it just this diffuse cloud, but instead it's these orbits around our nucleus, that the electrons can only exist in certain discrete energy levels. The analogy I like to use is a ladder, right? That you can think of the energy levels on an atom like a ladder. When you climb on a ladder, you can only ever exist and be stable on a certain rung, right? Can you exist between two rungs on a ladder? No, you're not stable there. You'll just fall to the closest lower energy level or lower rung in that case. So you can think of these energy levels as rungs on a ladder that electrons are allowed to reside in. So our Bohr model was our next step to allow us to describe the phenomena that we were seeing, the line spectrum coming off of our atoms. All right, so that is the first model, or sorry, the first postulate or the first kind of criteria of the Bohr model. So why do we need rungs on a ladder? The reason is without rungs on the ladder, without energy levels, the electrons would just crash into each other with the protons in the nucleus. Think about it. Protons are what charge? Positive. Electrons are what charge? Negative. What do positive and negative things do? They attract one another. So if you just have a positive and a negative thing, just like floating around, what's going to just naturally occur? They're going to attract into one another. So what's stopping an electron from just funneling in and colliding with the nucleus? And that's what the Bohr model does. It allows the electron to safely and be stable away from our nucleus, all right? So the idea here is we need energy levels present, or else the atom explodes on itself. And then we have like nuclear fusion happening, and that's not good. So when there's no rungs on the ladder, think about it like a ladder again. If you pick me up and there's no ladder and you drop me, what happens? Am I stable up there in the sky? No, I'm not. So I just come plummeting down to the Earth because I'm not stable. And that's exactly what happens to this electron. It just orbits around the atom and then it explodes, right? Not stable when we don't have energy levels. But once you put the ladder there and you pick me up and you drop me on the ladder, do I stay stable up in that higher energy level? Yes, once that ladder is there. And so the same idea with the electron. Once you have that stable ladder present, now your electron can orbit safely around your nucleus without crashing into it. We need those energy levels there, or else our electron will just collide with our nucleus and a nuclear explosion will go off. And we don't want that. So that's what the Bohr model says. We need these energy levels there. And this is the spacing between those energy levels. Here, n equals 1, we call this the ground state because it's the most stable, just like, a ladder. While these higher energy levels, we call this excited states. Excited states. Okay? We can promote the electron to higher energy levels, and the electron can come back down. All right? And we call those transitions. And that is what the next postulate says. All right, so the first postulate just gave us the rungs on the ladder for electrons to exist safely. But now, why is light involved? Why are we talking about light so much and electrons? Well, that's what the second postulate comes from. The second postulate says that light is involved with an atom when electrons undergo transitions, meaning that the electron moves. Okay? When your electron's just hanging out chilling on n equals 1, it is not absorbing, it is not emitting any light. But as soon as it gets promoted to a higher energy level, energy is involved, so light is involved. As soon as the electron comes coming back down to a lower energy level, light is involved. All right? So light is only involved when the electron moves from one energy level to another. Okay? When it climbs up the ladder or when it falls down the ladder, light is involved. But if it's just chilling in the middle of the ladder, not moving, is light involved? No, just when it moves. So here is a bunch of equations, but we're actually never going to calculate anything. Again, I like to do stuff conceptually because it's harder. I think my pencil is dead. Okay, so the first equation that we see here, is it dead? So I have to use my laser pointer. Yes, okay, so the first equation that we, oh, too much coffee. This first equation we see here is the energy of one rung on our ladder. One rung, so it's just the energy of one energy level. Not super useful for us. What we care about is what is the energy difference between two energy levels, because the energy change of our electron when it undergoes a transition is related to the energy of the photon that is either absorbed or emitted during that process. So this is why light is important. It's what's interacting with matter, promoting and being emitted from atoms when electrons undergo transitions. So this equation, not super important. It's the absolute energies of each of these rungs. What is important is the change in energy or the difference in energy for these different rungs, because the change in energy is equal to the energy of the photon involved in that transition. All right. So if we have a big drop from n equals 2 to n equals 1, then that means a large amount of energy is involved in that process. Though if I just have a tiny drop, all right, like a tiny drop in energy from a higher level to a lower level, then the energy of the photon that's involved is also very small. All right, so the energy difference of these transitions matter. And so you see that here. Energy of your photon is equal to the absolute value of the energy transition of your electron on your atom. And so that energy of the photon still follows the exact same equations that we studied before, hc over lambda or whatever. All right, and so the beautiful thing about Bohr's model is once we put these rungs on the ladder, we got energies of the different rungs and calculated the energy differences between the different rungs on the ladder. What we got out were energies that related to these 4 different, or 5 if you have really good eyesight, 4 or 5 different visible lines with certain energies. It matched up with the Bohr model that the Bohr model predicted. All right, that it's the energy differences between energy levels that an electron moves across is related to the energy that's involved in these different line spectrums. And so the spacing between energy levels is different for every atom, and so that's why we have different lines that come out for every atom. All right, so kind of putting everything together, you see in the visible spectrum, so us as humans, our detectors on our faces only detect visible light. Right? So atoms, they actually emit much more than just visible light, but just to us humans, we can only detect the visible ones. So right here, this is just a small sliver of the spectrum that comes from this element. What is this? Hydrogen. There's many more, but the only ones that are pertinent to us are the visible ones. So what we see here is we have some high energy photons near the 400 region. These are high energy photons. So that means it was a large transition involved, right? Because high energy photons, short wavelength, means high frequency, high energy, versus 600 nanometers, that's lower energy light. So what changes about the wavelength? It gets, so low energy is long wavelength. So we see that relationship here. Again, all the wave nature of light comes out here. Low energy photon means small energy transition, long wavelength, versus over here with short wavelength. Okay? So these lines that we see are specific transitions of our electron. Okay, so now let's talk about, what kind of light is involved with this transition. All right, so if a hydrogen atom or any atom at all absorbs a photon is just pure energy. So if the atom absorbs energy, what do you think will happen to the electron? Will it get promoted higher to the ladder, or will it fall? It's going to go higher, so it's going to climb up the ladder, right? So when light is absorbed, electrons are promoted to higher energy levels. Versus when an electron falls to a lower energy level, your N level decreases, your atom loses energy. This is an exothermic process. Light is actually emitted. So what we're seeing when we look at these line spectrum, we are looking at the emission of light. The emission of light. So we have to be careful of our language here. Is the electron getting promoted and absorbing light, or is it falling and emitting light, all right? So those are the two scenarios. And then we can relate it to energy based upon how big or small the transitions are. I'm going to point out real quick. Do you see these energy levels? I have it blown up bigger here. So 4, 3, 2, 1. So is this like a normal looking ladder? Ladders typically have rungs that are what? Equally spaced? Okay, so are the rungs here equally spaced? No, they're not. So a special concept about the Bohr model is as we get to higher n values, the energy levels converge on one another. They get closer and closer together. And that's what you see here. So if I wanted to draw n equals 5, it would be even closer. N equals 6 would be even closer. And the reason is if you look at the equation for energy of each level, as n increases, n is in the denominator, so that's the reason they get closer and closer together, where the limit is for this equation. Okay, so let's hear all the equations. The math is not important, it's actually the concepts here. So here's my energy level diagram. I've drawn in 3 different transitions. I want you to match the transitions, A, B, and C, and their significance to the different wavelengths that you see pictured here. So can you do that? So wavelengths 1, 2, 3. Can you relate each of those wavelengths to transition A, B, or C? So let's differentiate these. Let's look at the wavelengths. How are these waves different from each other? They have different wavelengths, yeah. Okay, so it looks like 1 has the wavelength that's the shortest, right? If you look at peak to peak, shortest. Peak to peak, they're closest together, while wave 2 has the longest wavelength of light. Okay, so remember, there's 3 ways we can talk about properties of light: wavelength, frequency, and what else? Energy. So it might be better for us to think about, instead of these wavelengths in terms of just their, property of wavelength, can you tell me something about their energies also? Which wave has the highest energy? I, yeah, because short wavelength means large energy. So because the equation is E of your photon is hc over wavelength, so energy of your photon in I is your largest, while it is your smallest in 3. Okay, so now can you relate these to the transitions? Which transition is the first wave, I? A, B, or C? What do we think? Who thinks C? Okay, who thinks A? Ooh, yeah, see, it's 50-50. All right, so let's go back a step here. So what is this? Is this a high energy photon or a low energy photon? High energy, okay? So energy is related to how big our drops are, how big our gaps are in our energy levels. So if we look at C and A, these 2 transitions are vastly different. One is a small drop. So what is that, a large energy difference or a small energy difference? Small energy difference. So C is actually which wave? The third one. So this is C, because that's the smallest energy. A is actually that first wave, because it's the highest energy transition. All right, highest energy drop. Versus B is your middle one. All right, but the A and C one, those were the important ones that often get confused. All right, just think about it. If you dropped me from a very high energy, like a high height, if you drop me, that's what, a small transfer of energy or a large transfer of energy? That's pretty large, okay? And so that's what we're looking for here too, but relating it to energy of photons given wavelength of light. All right, so this is definitely a conceptual question that doesn't require any math, but understanding relationships between energy a photon's wavelength, and also the significance of our Bohr model here. Okay, let's do one more that is really common on the exam, and then I'll do a demo. Okay, which of these electronic transitions on a hydrogen atom corresponds to the emission of a photon with the shortest wavelength? Okay, so it's all about reading comprehension here. What's the question asking? What am I looking for? So first, let's just read this. So I know that I'm picking a transition from different energy levels. So emission of a photon. Am I looking for an electron jumping or one that's falling? When is light, a photon, emitted? When an electron falls. Yes, because a photon, light, is pure energy. So energy is released when that electron falls. So emission of a photon, we are looking for an electron falling. So we can eliminate probably half of these, right? We can eliminate A, because in A, the electron is jumping up. So this is actually absorbing light, so A is not right. What about B, 2 to 3? Is that absorption or emission? It's also absorption. So we're looking at 4 to 2 or 3 to 1. We need to decide which one it is. Okay, so we're looking for an electron falling. Shortest wavelength. So what does that imply about energy? Highest energy. So we are looking for the highest energy of our photon. So we are actually looking for the largest fall. Largest fall. Okay, so that means now I need to draw an appropriately spaced energy diagram. Okay, so I'm going to draw 2, and you tell me which one's appropriately spaced. 1, 2, 3, 4. So this is n equals 1, 2, 3, 4, or 1, 2, 3, 4. 1, 2, 3, 4. Which one's appropriately spaced? The first one or the second one? The second one, yes. And also, because here's the thing, the reason, you can't answer the question actually if it's the first one. So let's just try it, right? So draw in the transitions for C and D. If we go from 4 to 2 versus 3 to 1, these rungs on the ladder are equivalent to energy. All right, I try to, the farther the drop, the more energy that's transferred here. So, like, is it obvious which transition is bigger? No, because both of them both go down 2 rungs. And so if you draw the energy diagram incorrectly, you can't answer the question. But so this is incorrect, you can't answer it like that. One, the hydrogen atom does not look like that because you're incorrectly spacing those energy levels. So let's use the correct diagram. So 4 to 2, that's C, versus 3 to 1. So which one is it? Which transition emits a photon with the shortest wavelength, C or D? D, yes, because it's the largest fall. Okay, I love questions like this because there's so many ways I can ask it with not really changing much. Instead of saying emission, I could change it to absorption. So if I said absorption of a photon, what would you look for instead? Jump. Yeah, you want to find the one where the electron jumps. What if I said smallest frequency? What would that mean? You are looking for a big gap or a small gap? Small gap, yeah. What if I said longest wavelength? Big gap, small gap. Longest wavelength. Small gap, because that means small energy. In the end, everything comes back to energy, all right? And so emission versus absorption, different. Okay, so let me go back here. All right, so back in this diagram, we have those transitions A, B, and C. So tell me, how is light involved in these transitions? Is it emission or absorption in these pictures? Is light being emitted or absorbed? Emitted, yes. And so, what is the big difference between emission and absorption? So, the reason that grass is green, why is atomic structure important? The reason grass is green is because grass absorbs all the visible light except green light. So when we look at grass, all of the colors of the rainbow except green are absorbed into the molecules, but then green light is reflected into our eyes. That is why grass is green. That's why the sweater you're wearing is blue. It's because it absorbs all the colors. It has electronic transitions equal to all of the colors except blue, for blue to be reflected back into our eyes. So that's absorption. Absorption tells us why things are a certain color. But emission is a little bit different. Emission, kind of like, the glowing effect of lights or a neon sign, little bit different. I said before that every element has a different line spectra. Every element emits different colors because every element has different energy levels in its Bohr model. So we are going to look at different elements line spectra. All right. Okay, no, not that. Let's just turn off the lights. Oops. Turn off the lights. Look at the colors of emission of light. So what we're going to do is I'm going to get the electrons in different elements to fall. And the only way I can do that is if I excite all of the electrons at once. All right, so if I excite all the electrons by using fire, okay, I can throw all the electrons in the air. The electrons will fall back down, and when they fall, it'll emit light that we will be able to see emitted here. All right, so the fire is necessary to excite all the electrons, but what we are seeing is the emission of it coming back down. So let's try this. Let's try this. Ooh, okay, all right. This is kind of dangerous, so let's see. All right, so like I said, every element has different colors, so I have 6 different ones, so let's see what happens. Okay, so let's do a cool one. Let's do lithium. All right, so this is the color of lithium, all lithium. Ooh, did you see that? Ooh. All right, so what color are we seeing? Red, and that red color is from the electron falling to between 2 energy levels where the energy level is different. The difference is equal to that of red light. All right, so that is lithium. All lithium will be that color. All right, so that's lithium. Let's look at strontium. Ooh, also red. So a little different. Ooh, it looks spicy. All right, so there's strontium. Let's see. This one's nickel 2+. It says peach, but I don't know about that. Ooh, yeah, this one's kind of hard to see. They didn't bring me sodium. I'm surprised. Because has anyone ever boiled pasta water and accidentally let the pasta water burn over or boil over? And then if you have a gas stove, you see all the flames come up and it turns what color? Bright yellow if you let it boil over, and that's due to the presence of sodium ions if you salt your water, and so you'll see it very bright if you let it boil over. Okay, so let's do potassium. Okay, this is lavender. I'm not sure how good it is. Ooh, if you look really closely, you can see the purple. Do you see it? Kinda. Yeah, you can see the purple. All right, that's potassium. Boric acid, they say, is green. I'm not sure about that. Okay. Oh yeah, that's really hard to see. No, okay, nope, that's not working. All right, and then copper, save for last. Usually you can see this. There we go. Yeah, copper. So something I like to do whenever I do plumbing work in my house and, cut copper pipe. Well, one, copper is kind of expensive. You don't want to just throw that stuff away, but I usually save scrap pieces after cutting it, so whenever I make a bonfire outside, I can throw the copper pipe into the fire and you see nice green flames just like this. So whether it's in a spray bottle dissolved in methanol or in pipe form, you will still see those green flames due to the electronic structure of copper has energy levels exactly equal to the energy of green light. And so that that is why this is green. All right, so copper emits green, but does it look green? Copper, like a piece of copper. No, it doesn't. And the difference is because of the energy levels there of electrons falling equate to emission of light that we see here. Okay, so electrons, light, burning stuff. Let's turn the light back on. Boom. Okay, all right. Okay, so what's the answer here? Why does this atomic structure matter? Why is grass green? A, B, or C? It is C, yes, it is C. Because grass absorbs everything except, oh my gosh, my pen is broken, or it's dead. Okay, it's C, you know that. Okay, so we have 40 more minutes, dang. Okay, so let's talk about the wave nature of light now. There we go. Wave nature, or sorry, we already talked about the wave nature of light. Then we talked about the particle nature of light. That was our photon, energy of our photon. So electrons have mass. They have a certain energy. And so what kind of brings us into the quantum realm and where everything starts to change is when we start thinking about electrons a little bit differently. So light is a wave, right? You learn about it in E and M. But using E equals hc over lambda, we learned that light is also a particle. It's a photon. So if an electron is a particle, is it too much of a stretch to say, okay, if an electron is a particle, it can also be a wave? If light can be a wave and a particle, why can't a particle also be a wave? Right? Isn't that like some math property? Like the commutative property or something? Yeah. So that is what de Broglie said. All right. So Louis de Broglie was this, I don't know if he was a genius or just really crazy, kind of proposed the idea, what I just said, that an electron is a particle but can also have wave properties as well. And this is an instance where someone came up with a theory. Everyone didn't believe them. He wasn't believed. He was like called crazy. And then years later, they did experiments that confirmed their theory. And that's what de Broglie did. So his PhD thesis was the de Broglie wavelength equation that said all matter has a wavelength. He was kind of ridiculed. No one believed him. I think it's because no one understood it. Right? It was just so far out there. And it took many, many years later for them to confirm those ideas that electrons are, in fact, waves. And they are particles, but they also have wave characteristics as well. So here's the de Broglie wavelength equation that actually says all matter has a wavelength, where it's related to Planck's constant, same one as before, divided by its mass, divided by its velocity. Electrons have mass. Electrons also have velocity. They're zipping around your atom, so they have a wavelength. But specifically for electrons, it's really important. The wavelength is really important because are electrons really big or really small? Small. So if you have a small number in your denominator, what kind of number comes out? A pretty big number. So when we look at electrons, they're so small that their de Broglie wavelength starts to matter. And that's why stuff gets really weird when it's small. No longer can classical physics completely describe a situation. Classical physics is great for large objects, things that have a lot of mass. Things that have a really small de Broglie wavelength, that doesn't really matter and you can just ignore. But for an electron, where the mass is really, really small, its de Broglie wavelength is really big and we can no longer ignore it. And that's what is important here, all right? So just kind of to prove it to you, all right? So light. Think about the light's wave properties. One of those properties is, I should charge my pen while I'm running around doing demos. Charge, okay. One of the properties of light is the property of diffraction, right? That the idea that light is a wave, if they hit a diffraction grating at different angles, we can get a pattern come out. It's like, do people still use CDs? I don't know. But if you take the back of a CD that has a grating on it, if you take a laser pointer on the back of a CD, you can see patterns come up. So I can show that here for you. Here's, I don't know what's going to happen here. All right, so here's just the regular laser pointer, all right? It's a bunch of photons in a coherent stream, but now I'm going to put some gratings in front of it, and we can see the wave properties come out. So you see the patterning come out, and this can only happen when things, we can consider them waves. They're hitting these diffraction patterns differently. And so I have different patterns here, all right? Again, this is the idea of constructive and deconstructive interference when they're hitting the grating. Here's this one. You see that, right? Yeah, okay. This one, and this one's neat. See? It goes across the whole room. All right, and something cool with gratings. Oh, you can't see it. They said they just changed the light on the green one. Okay, I think I broke it. So the idea of diffraction, all right, constructive, deconstructive interference. That is what kind of property? A particle property or a wave property? Wave property. So the experiment that kind of highlighted the importance of the de Broglie wavelength and the idea that electrons are also waves is, okay, light can be diffracted with a grating. Turns out electrons can also be diffracted. And that would only be possible if electrons behave like waves. If they were just particles, we would never see a diffraction pattern like this. So electrons, yes, they're a particle, but they also have wave properties, and we prove it using electron diffraction. So it's, again, basically what I just did, but on a very, very smaller level. We use a smaller grating, but we do see electron diffraction, so constructive, deconstructive interference of our electron. The idea of the double slit experiment, all right? The double slit experiment is where we have two slits, right? If you shine light through it, like a laser, you get constructive, deconstructive interference if there's the two sources come in, so the wave properties come out. And so what we see with electrons, when we do the same thing with electrons, sometimes we see the wave properties of the electrons, sometimes we see the particle properties of electrons. And kind of the cool thing about the double slit experiment is that you can never see both at the same time. It's only one or the other. So if you go to the subreddit physics memes, literally 50% of the memes on that subreddit are about the double slit experiment, and that's about the dual properties of electrons. Are they behaving like waves? Are they behaving like particles? And that's kind of the joke behind all of that. Okay, so what is the issue with electrons being waves? Okay, so we're kind of breaking down classical physics. Classical physics is fine enough for things that are big. But again, electrons are small. They have big de Broglie wavelengths that we can no longer ignore. So we need a new type of math to accommodate for it. All right? So the big difference here, and where the uncertainty principle comes into play, is that in classical physics, we can know everything about everything at any time, all the time. So if I took a football and kicked it across the room, you could track the location of that football at any point in time. You can track its location, its velocity, its trajectory, everything. You can know everything about that football at any time. It's like when they, blasted astronauts up to space. Those are big, big things. They calculated trajectory, velocity, mass, all those things, right, about the spaceship. That's us sending men to the moon. But here with electrons, we can't have certainty all the time when things are very, very small. That's the big difference when things are small, right? In the quantum realm, things are very small. It's impossible to know two measured values at the same time when they're in different eigenstates. That's the definition, all right? And so when things are really small, we can't know for certain, like two different values, such as energy we can't know its location and its momentum or its velocity at the same time, right? We have to have a little bit of uncertainty there. And so there's an analogy I like to use. Pretend we're at the NASCAR racetrack, right? They're going around in the thing real fast, right? Okay. Pretend we're at the NASCAR thing and we take a picture of them. Okay, we take a picture, snap a picture of them going around the track. When we snap that picture, what did we measure at that moment? Position, their position. Once we take that picture, we located their position right at that moment. But with that picture, do we know anything about their velocity at that moment in time? No, because what we've done is collapse the wave function. We now know their position with certainty, but therefore we know nothing about their velocity. Right, so that's kind of the idea of the uncertainty principle. We can know a lot about one thing, but be uncertain about the other. Or know a lot about that other thing, but be uncertain about the other. Or just kind of know both not so well. But we can't know both with absolute certainty at the same time. Okay, here's the same analogy. So we're still at the race car track, right? Okay, pretend I'm sitting there with a radar gun, right, to track their velocity. They zoom by me and they go, how fast do they go? I don't know, like, okay, how much? Okay, so they're zooming past me at 700 miles per hour, whatever, I don't care. Okay, so at that moment when I track 700 miles per hour, I know their what very well? Their velocity, their momentum, because their mass isn't really changing that much during the race. But what did I lose sight of the moment I tracked their velocity? Their position, yep, because they zoomed right past me. So that's the idea, that we can't know both at the same time with absolute accuracy. And so why this matters is because the Bohr model violates that uncertainty principle. That we were saying that, oh, that electron just orbits right there in a certain energy level. That's actually kind of wrong, all right? So what is correct here is the Schrodinger model, and that is the 100% correct view of our hydrogen atom. And what it just does is it smears the allowed positions of the electron in different places. So no longer is it certain rungs on a ladder that an electron can be. It's more of these certain areas that an electron can reside around an atom. So what we do is kind of make their location a less specific. All right, so we basically make these probability diagrams or orbitals of where electrons can be found. All right, so we say that the energy of the electron is quantized. We know that precisely, but the position we describe in terms of probability with a large uncertainty, and this is where our orbital shapes come from, S, P, and D. If you've taken chemistry before, hopefully you know when I say an S orbital, you think of a what? Like a sphere? A p orbital looks like does it look different? Kind of looks like a dumbbell, okay? Versus a d orbital looks like a butterfly, right? And so these are the different shapes, orbital shapes, where our electron can reside, and this does not violate the uncertainty principle because we're letting the electrons live in a large area, right? And so this is the uncertainty principle, right? Uncertainty in x times the uncertainty in velocity has to equal some minima, which is related to Planck's constant. All right, okay, so yeah. So the idea that electrons are very hard to locate with high precision is where Schrodinger's cat comes from. Where so the theoretical kind of thought experiment behind Schrodinger's cat is Schrodinger himself, when he solved the Schrodinger equation, he came up with this. That the idea that electrons are hard to locate and understand with high precision. So the thought experiment he came up with was pretend you have a box that has a radioactive substance in it that randomly may trigger a poison to go off. But you don't know if the poison goes off. So imagine you put that trap into the box. It may randomly go off, you don't know, and you put a cat in there at the same time. And you close the box and you walk away. And if you think about that box, what is in that box? One, you don't know if the trap went off or not. So that means you don't know if the cat is dead or alive. And so his thought experiment was, okay, if I don't know anything about whether that the poison went off or not, the cat has to be both dead and alive, because you don't know until you open the box. Once you open the box, what you do is you collapse your wave function, and now you know for certain whether the cat is dead or alive. So the idea when the box is closed and the cat is in with the poison and you don't know which one went off, the cat has to be both dead and alive before you open the box. And that is where Schrodinger's cat comes from. You can't know too much about anything at any certain time is the whole basis of quantum theory. Yes, and so cool things about like Breaking Bad, all right? His like bad boy nickname was Heisenberg, right? Because he's like shifty. I don't know, I've actually never watched the show, okay? So Heisenberg, like Heisenberg's uncertainty principle, so I don't know if his character matches that. Does it? Okay. Okay, is there some meta stuff happening there? Yeah. And so, yeah, Heisenberg uncertainty principle. Yeah, cat being dead and alive at the same time. So this is the experiment, right? Cat's in the box. We don't know if this poison's going to go off or not. But the thing is we can't see inside the box. So when it's closed, it's both dead and alive until you open it. So it's cool. I have this poster outside my office. It's a painting. I know it's hard to see. It's of the cat. It's both dead and alive at the same time. But if you go to my office, the painting is drawn with Heisenberg's uncertainty principle, just the lines of it. So it's not like drawn. It's used with like numbers and stuff. So if you look closely, you can see the numbers of Heisenberg's uncertainty principle written in it. And that's nerdy art, you know. And so it's outside my office. I like it. It fits my aesthetic. Okay, yeah, so the idea that electrons hard to locate with high precisions, where Schrodinger's cat comes from. This is also called quantum superposition, where something is in two places at once until you open the box and you observe it and you collapse the wave function. Okay, so that is Schrodinger's cat. So hopefully you can understand and get along with physicists and chemists alike. Okay, so now with all of the theory behind us, electrons are hard to locate. This is where these orbital shapes come from. When I say s orbital, p orbital, d orbital, those orbital shapes are probability maps of finding an electron so we don't violate Heisenberg's uncertainty principle. All right, so this idea, electrons can live in these certain spaces, and each of these orbitals, each of these probability maps relates to a box on these energy level diagrams. And we'll soon start filling these energy level diagrams very soon here. So each of this shape, this s orbital, is related to this block in our energy level diagram. In each box, you can put 2 electrons in it. And the reason is because of quantum numbers and solving the Schrodinger equation. All right, so here's the Schrodinger equation. Requires a new type of math. We're not going to study it, but really what this says is that the kinetic energy of your system, because if you look closely here, you see like a mass value, mass of particle, how the wave function changes from one place to another. This is very much like kinetic energy, 1/2 mv squared, mass times velocity squared. So here we have this kinetic energy term. We're adding it to, describes forces acting on a particle. This is potential energy, equals how the wave function changes with shape and time. So this is basically our overall energy of our system. So really, this is no different from classical physics. So kinetic energy of your system plus potential energy of your system equals total energy of your system. But we just use different types of mathematics to solve for it, wave functions specifically. Because remember, electrons are waves, so they can have a wave function, right? So when you solve that, what comes out is a bunch of polar coordinate solutions. And so these polar coordinate solutions are how we get our quantum numbers. But that's not important. This class is not about solving the Schrodinger equation. It's about how scientists, came to a solution to a problem that they were observing, came up with a solution, and the the results, the conclusion from their solutions, out comes the quantum numbers that we know that describe where electrons are. So after solving the Schrodinger equation, we have quantum numbers that describe the energy of where electrons can be, their shape, and their orientation. And we'll talk about all 4 of those quantum numbers here in a second. But again, the significance is where those quantum numbers come from is from solving Schrodinger's equation, which I only ever did once, and I did very poorly, okay? Because mere humans can only solve the Schrodinger equation for the hydrogen atom because it's just 1 proton, 1 electron. But once you add a helium, and there's 2 protons, 2 electrons, and then some neutrons thrown in there. Now it's a very, very complex system, and you can't solve it anymore. So we send it to supercomputers to solve it for us, just once we get to helium, all right? And that's what we do nowadays. No one solves the Schrodinger equation. We all just send it to the supercomputer to solve it for us, to find a local minima. All right, so yes, we're going to talk about quantum numbers, memorize this table, but we're going to basically go through the table in bigger slides here. All right, so the first quantum number is the size quantum number, or the principal quantum number. All right, so this describes the energy of the electron, the size. And so these principal quantum numbers, they are integer values. So they start at 1 and go up 1, 2, 3, 4, 5, etc. So those are the allowed energy levels of our electron. This is the same as the rungs of the ladder in our hydrogen example. All right. Okay, so as n increases, we see a couple things. We see, what do I want to say? I was supposed to write something here, but I forget what I was supposed to say. As n increases, we see size of your orbital increase. Okay. As n increases, what else? We see the energy of our electron or that orbital also increase. All right. So here's some some examples. So here is the box for a 1s orbital, or for an n equals 1. And then here we have the energy for n equals 2. And so if we compare an orbital, or the location where we'll find an electron in either one of these energy levels, we see that in n equals 1, we're restricted to a smaller area, versus n equals 2, it's much larger, all right? So our orbital increases as n increases, so like a larger space for the electron to hang out. Also, the energy increases, all right? So yeah, that n principal quantum number relates to size and energy. And so those are whole numbers. They start at 1. So n equals 1, 2, 3, 4, etc. So that's the first quantum number that we can have for an electron. The second quantum number, L, or our secondary quantum number, this says it identifies the subshell, but I like to think of the L quantum number as shape. Okay, the L quantum number tells us our shape. And so the possible L values we can have, the possible shapes we're allowed to have, depend on the n value that we're in. And so here's the rule. All right, so for any particular n value, the possible L values always start at 0 and are all the integers up into n minus 1. So what that means is if I have an n equals 4 energy level, my possible L's I can have are 0, 1, 2, 3, and that's it, because n equals 4. So I can have all the integer values up until 1 minus 4. So for n equals 1, what are the possible L values? Just 0. That's it. And that's what we see here. For an n equals 2 energy level, what are my possible L values? 0 and 1. And so we see 2 different shapes here, S and P. All right. Okay, so these L values, 0, 1, 2, 3, 4, etc., also have letter designations, and these are where our S, P, D subshells come from. So also memorize this table. If L equals 0, this is an S orbital. An S orbital looks like a sphere. If L equals 1, that's a P orbital. It looks like a dumbbell. A D orbital, that's L equals 2. It looks like a butterfly. And then we can keep going. 3 is F orbital, 4 is G orbital. We add a lot more lobes here, but those aren't really common. All right, so you might be wondering, oh, like, why is it so random these numbers actually have letters and shapes that go along with them. So remember, these numbers were solutions to our Schrodinger equation. These quantum numbers, they were solutions in polar coordinates. So these numbers are actually the number of angular nodes inside of these particular shapes. But how I describe it, these numbers tell us how many times, if an orbital were a balloon animal, how many times we would twist it to get that shape, right? So pretend we have just like a balloon, and we have an L of 0. How many times do we twist the balloon? 0 times. What shape do you have? A sphere. Is that what an s orbital looks like? Yes, it does. Okay. So L of 1 means how many times we twist the balloon? Once. So take the balloon, twist it, what does it become? It looks like a dumbbell, right? Yes. Okay. So then a d orbital, this one's kind of weird. We have to twist it twice. So what do? So we take the balloon, we twist it once, but then what you got to do is like fold it in half and then twist it again. And that's how you get the butterfly shape come out, kind of. That's where my analogy breaks down, all right? And so what you see here, you know, we don't have to understand angular nodes, but there is a significance to these numbers. It's how many, angular nodes there are within these particular shapes. We don't have to know the angular nodes as long as we know the general shapes here. S orbital is a sphere, P is that dumbbell, D is that butterfly. All right. Okay, so let's continue here. So if we have an n equals 3 and an L equals 1, we call this a 3p subshell, right? Because the n of 3, there's the 3, and we remember L of 1 is related to a p orbital. So we call that combination a 3p orbital or 3p subshell, right? So there's also a 3s and a 3d, but those have different L values, L of 0 or L of 2, right? So let's go through this. Let's name all of the oh my God, okay, never mind. Name all of the subshells that possess n equals 5. So let's name all of the possible L's that we can have if n equals 5. 0, what else can we have? 1, can we have more? 2, 3, 4, tell me when to stop. Stop, okay, perfect. Right, that's not our answer though, we need to interpret it. So a orbital or a subshell with n equals 5 and an L of 0, what do we call that? A 5s. What about that L of 1? We call that a 5p. L of 2, that's d, so it's 5d. Then 5f, and then that 4 is a 5g. So those are all the possible subshells in an n equals 5, okay, related to those L's. Why is there no such thing as a 2d subshell? 2 implies that n equals 2. D implies what? L is equal to 2. Is that possible? No, it's not. The minimum n that we can have to have a d subshell is actually an n equals 3. So 3d is where your d subshell starts. Okay, so that is your quantum number or your secondary quantum number. This tells us our shape. All right, so the next one is your magnetic quantum number. This is what determines the overall orientation of your orbital. Basically, in practice, this is what tells you how many boxes each subshell has. Because if we look closely here, our s orbital has how many boxes? 1. P orbitals, or P subshells, have how many boxes? 3. D subshells have 5. How many do you think F has? 7. What about G? 9, yes. And there's a reason. It's due to how many magnetic quantum numbers there are, how many orientations there are for each orbital. So here is the rule. Depending on which L subshell you're in, so S, P, D, L of 0, 1, 2, etc., the possible number of orientation depends on the L number that you have. So the rule is all of the positive to negative integers between your positive L and negative L. So what that means is an L of 0 or an s orbital can only have one orientation, an ML of 0, because plus or minus 0 is just 0, and there's no integers between that. So in practice, what this means is there is one box in an S subshell. One box, because there's only one ML number, versus a L of 1, this is a P subshell. The integers we can have are -1, 0, and +1. So how many numbers are there? How many orientations are there? 3. So how many boxes are there going to be? 3. So we see P subshells have 3 boxes to put electrons. Okay, L of 2, what kind of orbital do we call that? D. So what are the possible orientations we can have? -2, -1, 0, +1, +2. So tell me, how many boxes does a D subshell have? 5. 1, 2, 3, 4, 5, all right? And you can keep going, right? F will go all the way from -3 to +3, that's 7 boxes, and then so forth. But we're mostly going to worry about S, P, and D. So that's what explains how many boxes there are. These are the different orientations, unique orientations that an electron can have in these different orbital shapes. Here's an example. S orbital, that's the one box I was mentioning. P orbitals, there are the 3 different unique orientations aligned on the XYZ axis. Here are the D orbitals and the butterfly shapes, the unique orientations within their 5 different orientations. Okay, so in general, there are this many orbitals, 2L plus 1 orbitals in a subshell. So how many orbitals, or think about this, it's how many boxes are there in a 2S subshell? How many? You can also look over here. 2S has 1, yeah. 1 orbital. So then how many orbitals does a 3S subshell have? Also 1. So what really matters here? It's the S. The S is what, or the S or the P or the D is what dictates how many boxes we're allowed to write. All right, how many orbitals in a 2P subshell? So how many boxes? 3. All right, and then 3D? 5. 1, 2, 3, 4, 5, so 5. And so really the number out front, the N value does not matter. It's the L value that dictates how many orbitals we can have in it. Any D orbital has 5 orientations, can hold 10 electrons. Any D orbital. Doesn't matter if it's 3D, 4D, 5D, whatever. All D orbitals hold 10 electrons. Okay, so we built our boxes. Now let's put electrons in those boxes. All right, so in each of these boxes, we are allowed to put 2 electrons. And the reason is this is the last quantum number, the 4th one. And that is the spin quantum number, where an electron can either be spin up or spin down. And so when putting electrons in boxes, the only way to get 2 electrons in a box is if one electron is spin up and one is spin down. Because then we have different quantum numbers for electrons inside that one box, okay? And so this is called Pauli's exclusion principle. It's a rule for electrons and of life, is that no 2 fermions, which is an electron, cannot have the same 4 quantum numbers, N, L, M, L, and M sub S. So the idea here is if I have 2 electrons in the same box, they have the same N, they have the same L, they have the same M sub L, they cannot have the same spin. So one has to be spin up, one has to be spin down, and this is how we avoid violating Pauli's exclusion principle. But if you ask anyone what is electron spin, we're not quite sure about that one. It's just something scientists kind of made up and just said, sure, that sounds right. But the electrons aren't really spinning. We're not quite sure what it is. All right, so that's something you can look up. But in terms of just filling electron diagrams, it's fine for us to just put one spin up, one spin down. That's fine enough. Because one, electrons are not these 2-dimensional things that fit in boxes. They're much more complex. But this is just a way for us humans to visualize it a little bit better. Okay, so let's put it all together and determine what are all of the possible values of the 3 quantum numbers for an n equals 4 shell. All right? So remember, there's 4 quantum numbers, n, l, m sub l, and m sub s. So if we have n equals 3, what are my possible L values I can have? Do you remember those rules? We can have 0, 1, 2, anything else? 3, yes. So for each of these, L of 0, L of 1, L of 2, and L of 3, these are all different shapes, right? This is my S, P, D, F subshells. Each of these have additional quantum numbers, m sub l's. So I need to calculate the m sub l's for each of these, all right, the orientations. So what are the possible m sub l's for a s orbital, L of 0? We can only have 0. So that means how many boxes are in this s orbital? Just 1. Okay, what are the possible m sub l's for an L of 1? So a p orbital. We can have -1, 0, +1, so how many boxes? 3. All p orbitals have 3. D, so m sub l is -2, -1, 0, +1, +2, so how many boxes? Those are 5. 1, 2, 3, 4. Okay, that looks really messed up. Those are 5 boxes. And then finally, an F orbital. What are the possible m sub l's for an F orbital? -3, all the integers between negative and positive, that L value. So -3, -2, -1, 0, +1, +2, +3. So how many orientations are those? 7, so how many boxes can I have? 7, yes. So if I have 7 boxes, I'm not sure if that's 7, 7 boxes, how many electrons can fit in a single box? 2. So how many electrons can fit in an F orbital? 14, yeah, 14. 14, great. All right, so note, in any shell there are n, yes, possible orbitals. So count how many boxes total there are here. There should be 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. So there are 16 boxes. So there are 16 orbitals. So tell me, how many electrons can we fit in an n equals 4? How many electrons can we fit in all of those boxes? Is it 16? 32, yes, 32 electrons, because it's 16 boxes times 2 electrons each there, right? Those are all the electrons we can fit inside an n equals 4. All right, so that's determining what electrons are possible given certain energy levels, how far down we are on our periodic table. All right, we have 7 minutes. This is my last slide I will do here, just because I just want you to write it down, because we have a couple minutes left, but I'll pick up here on Thursday. The next thing that we're going to do is start placing the electrons. All right, we're going to start placing electrons in these boxes. And so typically we start from the bottom up, but we got to follow some rules. And the first rule here is off-balls principle, the idea that we want to fill lower energy levels first, available energy levels first, and fill them up to the top. So we put the electrons at the bottom, fill them up. The next rule that we have to follow for building electron configurations is Pauli's exclusion principle. So the idea that 2 electrons can't be the same spin in the same box. And the last one, and this one's probably the most important, is Hund's rule. The idea is when we're placing electrons in subshells that are the same energy, we want to do it in a way that produces the most stable arrangement of electrons. And so here are some examples of p orbitals. If I need to put 3 electrons in a p orbital, I want to spread those electrons out so they're all the same spin. So in this example, having the electrons all spread out, that's the most stable, while these arrangements are not stable because the electrons are spinning opposite directions, kind of repelling one another, and so that is not as stable. So Hund's rule, it's you spread out electrons before you start doubling up within there. So we will follow these rules and start doing electron configurations on Thursday. I'm going to point out, I'm going to do some skipping around a little bit, so I might, after doing electron configurations, I might jump ahead to chapter 7. And so I'll adjust homework as we go. It'll all be done before midterm 2, all right? Okay, so I'll see you on Thursday.